Welcome to the lecture on fundamentals of MIMO wireless communications. Currently, we are in the phase where we are understanding the wireless propagation channel. We have briefly looked into the large scale propagation effects. Currently, we are going to start our journey into the small scale propagation models, and we will start with the multipath propagation. So, in small scale propagation model, that means when we study multipath, the reference books again that we need to follow. Of course, there are many other books which are very good, but the ones which we will closely be referring to in this particular section are Principles of Mobile Communication by Gordon Stuber and Microwave Mobile Communication by Jakes. Most of the things that we do can be found almost directly in these two books, but again there are many other references which are very good. Whichever you feel comfortable with, feel free to follow those references. They are all quite similar. So, when we talk about the propagation channel, especially the multipath propagation channel, this is one of the most important parts of this particular subject. We need to understand the propagation thoroughly. We need to understand the models, because understanding of these channels is very critical towards design of transmitter and receiver. And if you see how MIMO communications have evolved, they have primarily become so useful mainly because the channel has been well understood. And one of the most important things is the multipath propagation channel. So, we need to understand it thoroughly so that we can design transmitter signals, as has been said earlier, as well as so that we can cancel the effects of the channel. For this particular part, we will make certain assumptions about the model that we consider. We would take a look at that part where the signal strength variation over few tens of wavelengths, that is the small scale propagation models. And the important assumption is that the mobile is moving with velocity v along the x axis, as can be seen in this particular figure. So, we will be having the mobile moving along this axis. This is the xy plane, and the move velocity is v, as given by this. The E field is along the z axis. So, that is coming out of the screen or out of the page on which we are writing, and theta n is the angle of incidence. So, we can look at it in this way, that there is a mobile and there is a transmitter. So, mobile is this is the y and x axis, to be very clear. Y axis, this is the x axis, and let us say this is the antenna. So, electric field is along this axis, z axis. Mobile is moving with velocity v along this direction, and theta n is the angle of incidence of the plane wave arriving. So, plane waves are arriving from the transmitter to the receiver, and although in this particular figure we have the radiator almost in straight line, it could be anywhere. So, we could have the receiver instead of this location. Yeah, we could have the receiver here. So, in that case this angle which this ray makes with this velocity is theta, you can say. So, this is theta n in this particular case, or if it is moving in this direction, if it is moving in this direction, then in that case this would be the angle of incidence. So, there could be reflections. So, this ray could be getting reflected, it could be coming in this direction. In this case, this is the angle of incidence with the mobile. So, that is the basic premise on which we are going to go ahead with the discussion. Right. And there is large transmitter receiver separation distance. So, if the separation distance is large, then we can make this 2D wave propagation assumption. Basically, if this distance of separation is large, so as the wave propagates, we almost have like plane wave arriving, and we can do a top view. So we can have a top view of this whole plane. This is the y axis, this is the x axis. So as if we can do a 2D model for wave propagation with this. Okay. So this is the typical picture. So we make it small, and we assume that since the mobile is moving in this particular direction with a velocity v, there is a Doppler which is introduced. Now this is from classical physics that we consider Doppler. So if Fm is the maximum frequency of operation, then Fd, that is the Doppler frequency from the nth path, this is the nth path, is if it is the Doppler frequency from the nth path is equal to Fm maximum frequency on the cos of theta n, that is the component of that frequency in the particular direction. So where Fm is v by c times Fc. Now this is pretty standard. That means the maximum frequency of Doppler shift is v by c, where c is the speed of electromagnetic wave or speed of light, Fc is the carrier frequency. So what we can clearly see that as v, that means velocity increases, Fm increases. So if Fm increases for a given value of theta, Fd increases, or the Doppler frequency increases, and vice versa. The max and mean value being plus and minus v by c times Fc. All other values would be between plus and minus f max or Fm. Moving forward, so we can now start taking a look at the transmitted signal. We'll consider the band pass signal. So what we will do is we will write S of t as the transmitted band pass signal is equal to the real part of S tilde t, which is the complex envelope of the transmitted signal, e to the power of j 2 pi f c t, where this is the complex envelope of the band pass of the transmitted signal. So this is the transmitted band pass signal, and this Re is basically Re of, let's say, Z is the real part of Z. Okay. So this is the basic model with which we will proceed in our calculations, and we will of course assume that there is a transmitter, there is mobile station, and the signal propagates through multiple paths. This is one of the most important things that we are going to see. So there are more than one path through which the signal propagates, and these paths could be because of reflection from building, could be because of reflection from moving vehicles, could be from lamp post, or could be from trees, could be from houses. There could be blockage, severe blockage due to a building, due to something being present in the line of sight. So end of the day, we are getting multiple signals arriving at the receiver, and what we are going to study is what happens to the signal when we add up these signals at this point of the receiver. So taking a careful look at the picture, this particular figure roughly explains what's going to happen. This picture is what's happening. So From the transmitter, as we have drawn, there could be path from the vehicle, there could be path from the building. This mobile could be fixed or it itself could be moving. Now, if the mobile is fixed and this reflector is moving, still we are going to experience Doppler effect because of the relative motion between the reflector and the mobile unit. So, with this model, we go ahead and say that the received signal, the noiseless received signal, okay. Typically in a communication system, you may have come across additive wide Gaussian noise channel, where we have the transmitter signal going through an ideal channel, nothing is happening, and there is only addition of noise. So, this is additive noise. It could be white, it could be Gaussian, okay, and then there is a receiver. And just to summarize, we usually consider this noise is being added because of analog components and of the receiver front end typically, and also due to conversion from the analog to the digital domain. Whereas in the current model that we are considering, we are just trying to see what happens to the signal in this point where it has almost not yet gone into the receiver, you can say, and these noise effects can be studied separately. So, as of now we are interested only in the channel effects, where there is a channel which lies between the transmitter and the receiver. So, there is a channel between the transmitter and the receiver, and we are interested in the channel. So, we are basically trying to look at what happens to the signal at this point, or what happens if there is no noise present. Later on we can always consider the effect of noise on top of these effects, and we can study the combined cumulative effect. So, the noiseless received band pass signal, so we are still considering the band pass signal, can be written as R of t is equal to, again, the real part of, we have this, and if we say that we are looking at this particular propagation, we will assume that each of the path has a propagation delay. So, let this path have a propagation delay tau 1, this particular path can have a propagation delay of tau 2, and so on, and this particular path in general has a propagation delay of tau n. In that case, the signal that is received from the nth path would be the one which was the complex baseband signal that was transmitted tau n units of time before the current time, because this is the propagation delay through which it has come. This signal is scaled by Cn, which is the amplitude associated with the nth path. That means, if the signal has started to propagate in this particular direction, then because of reflection at this point, there is a certain change in amplitude depending upon the reflection coefficient. If it has gone through this particular direction, because there is an obstruction, there will be a certain amount of attenuation through which the signal may have gone through. Again, because of this particular surface, the kind of reflection happening here would be different. If there is diffraction or scattering, there would be corresponding coefficient corresponding to the radar cross section and so many other things. So, in this model, we abstract the exact happenings at these points, whatever is happening, and we just model that there is some change in amplitude that has happened because of the different phenomena in the multiple paths. And this is the abstraction that we make. Now, instead of this, if we are doing a deterministic model, in a deterministic model we would have specified exactly what kind of surface is it on which this wave is impinging, what is the frequency, what is the irregularity, and what is the exact coefficient of reflection that happens. If there is a diffraction, we would try to calculate what percentage of power comes in this direction, what is the phase. If there is a refraction, accordingly we will take everything into account and solve the equation in order to get it. So, here we will try to do an abstraction and put Cn for the particular amplitude associated with the nth path. Now, with respect to the carrier, what we have is e to the power of j 2 pi f c is what we had when we transmitted the signal. So, the transmitted signal was s t equals to real part of s tilde t e to the power of j 2 pi f c t. What we have seen at the receiver, it should be s tilde t minus tau n, because signal takes tau 1 time to proceed, it takes tau n time to proceed. So, at any instant of time, if I am seeing the signal and that signal has come by the nth path, it must have started at a time which is t minus tau n, and it must have undergone a multiplicative gain which is C n. So, that is what is reflected in this expression. The signal in the nth path must have started tau n units of time before is that particular signal, and this gain contributes to the gain of associated with that path. There is f c is the carrier frequency. Now, the received signal is not only the carrier frequency, but also there is the Doppler due to the nth path associated with that path. Now, we instead of having j 2 pi f c, since the time it has propagated through is tau n, we have e to the power of j 2 pi f c t minus tau n. So, this is the expression of the passband received signal when it has come through the nth path. Again, if we go back and check this expression or check this situation, we have just written the signal which has come through the nth path. What we get over here is signals which have come through the first path, second path, third path, and so on for all possible paths. So, we modify this expression and we put a summation sign to indicate sum of n equals to 1 to capital N, indicating as if there are capital N number of multiple paths through which the signal has come at the receiver. At this point, we have the complete expression, and we would like to explore this expression a little bit more in order to see what lies in details. So, we could look at it further, and we could say this is a real part of the summation remains n equals to 1 to capital N C n e to the power of j 2 pi. Now, we would separate the carrier from the Doppler, because whenever we are studying communication systems, we have indicated before that we would like to study systems independent of the carrier frequency. So, we will just bring these terms separate, so that we can concentrate on the complex envelope of the signal, which is our main interest. So, if we collect these terms, we would have f d n of t and minus f c plus f d n of tau n s tilde t minus tau n e to the power of j 2 pi f c t. So, what we have is e to the power of j 2 pi f c t is separated. So, if we try to compare the expression with which we started, what we had here is s t equals to real part of s tilde t e to the power of j 2 pi f c t. What we have here is some signal, we have some signal and e to the power of j 2 pi f c t. So, if we have to study the complex baseband, or if you have to study the baseband, we can remove this part and we can focus on this part of the signal to study what has happened to s tilde t that got transmitted from the base station, for example, or a typical transmitter, and has undergone multiple path reflection, refraction or scattering, and has arrived at the receiver after this propagation effect. Now, in order to write it in a better way, we would define phi n as 2 pi f d n, that is the frequency due to the Doppler on the nth path, minus f c plus ftn tau n. So, this is basically the phase associated with the nth path, and we have this tau n term over here. So, if we look at this particular term, what we see is there is a multiplication of f c along with tau n. Now, this is very important for us to see. Tau n is the propagation delay of the nth path, and f c is the carrier frequency. So, if we say that let f c is somewhere around 900 megahertz, saying approximately equal to 900 megahertz, and we have a certain propagation delay. So, basically we have a certain propagation delay. Now, what we are trying to consider is the situation that this mobile has moved a little bit, or if we take this path, this vehicle has moved a little bit. In that case, the reflected path would be this second one, and we can call it T2 prime. So, what we would like to study is the impact of the change in path length on the phase of the nth path. So, to do that, if we say that let delta tau n, that is the small change, is approximately equal to 1 nanosecond. In that case, what we would find is the change in phi n is approximately equal to 2 pi. That means, it is undergoing full phase rotation because of just 1 nanosecond of change in path length. This is very important to capture, because a tiny change in the path causes a huge change in the phase. A huge change in the phase would cause the signal strength to fluctuate significantly. Now, when we have all these different paths coming to the receiver, slightest change in any one of the path is going to cause a huge change in the signal phase which is coming at the receiver. We are adding up all of these signals. So, what we are ending up is with a great change in the sum total effect of the signals coming from different paths. So, if we see over here, we should be able to write the received signal as the real part of the sum of n equals to 1 to capital N C n e to the power of j phi n, which is a function of time, s tilde t minus tau n e to the power of j 2 pi f c t. So, here we have captured the phases, the amplitudes, the phases, and the expression looks a little bit simpler compared to the above expression. So, we would rewrite this expression as we are continuing on a new page. So, what we have is r of t is equal to real part of summation n equals 1 to capital N C n e to the power of j phi n of t s tilde t minus tau n e to the power of j 2 pi f c t. This we could further write as real part of this whole thing. We would write it as r tilde t times e to the power of j 2 pi f c t, where r tilde t is the complex baseband signal or the complex envelope of the received signal for r of t. So, if r of t is the passband signal, r tilde t is the complex envelope, and the relationship between r t and r tilde t is real part of r tilde t e to the power of j 2 pi f c t is r of t. We had the same expression for s of t. So, if we look at these two expressions, they look very similar. This is the transmitted signal, this is the received complex signal. So, now since we have separated out the carrier, we should be able to concentrate on what happens to the complex signal that was transmitted at the receiver. We would of course define r tilde t is equal to sum over n equals to 1 to capital N C n e to the power of j phi n s tilde t minus s tilde t minus tau n. We could also say that let h of t comma tau n be equal to C n e to the power of j phi n. That means, we are taking these two terms, the amplitude and the phase of a particular path is being assigned to the variable h, which is a function of time, as well as tau n, which is the delay, where this phase term contains the time and the delay effects. So, we could write, if we take this, we could write r tilde t is equal to sum over n is equal to 1 to capital N h of t comma tau n multiplied by s tilde t minus tau n. If you look at this particular expression, it could also be written as in equivalent terms as if h t comma tau n having convolution with s tilde t, where h t comma tau n are the filter coefficients, or in other words, what we have is when the signal propagates through such a multipath, as has been shown in this figure here, where at each of the reflecting surface or where the wave hits, we have an amplitude C n, and because of the propagation we have a phase phi n. What we end up is as if there is some convolution with some sequence given by h t comma tau n along with the signal that comes through the particular paths. With this, what we see is that the multipath propagation, where at each surface where the incoming wave hits, there is a change in amplitude and there is a change in phase. What we can effectively write is that the received signal in the complex form is the same as the transmitted signal in the complex form. However, it is convolved with some coefficient which is capturing the effects of the channel. In the next lecture, we shall see some more details about what happens to the signal, or what is the typical behavior of such a phenomena when observed at the receiver for a particular transmitted signal. Thank you.